For today's lesson, I'm going to discuss solutions of differential equations. Similar to your algebra equations, differential equations need solutions also, no? So meaning, we're going to solve them. So remember, in your algebra, given an equation, you're looking for the value of the variable that will make the equation a true statement. But of course, there is a difference between a solution in an ordinary equation in algebra, with what? With the equation that we have in differential equation. When we solve a differential equation, expected the solution is also an equation. And that's what we're going to talk about today. What a solution of a differential equation is, how it looks like. Okay? So, occasionally, the derived mathematical model for a physical situation is in the form of a function or a relation defining a function that is free from derivatives but contains arbitrary constants. It is necessary to obtain a differential equation of such equation with the order equal to the number of arbitrary constants the differential equation contains. The function from which the differential equation is derived is called its solution. So what is a solution of a differential equation? So when you say solution of a differential equation, it is a function defined on an open interval of the form a less than x, x less than b, with the following, sorry, with the following property. So meaning such that when substituted to the differential equation, reduces the equation to an identity. So, okay? So that's what we mean by a solution of a differential equation. Again, take note that a solution of a differential equation is a function, meaning it is actually also an equation. Okay? Defining a function. And that function is defined on an open interval, single open interval, not union of intervals. If you have another interval, mm, mm, defining a function, so it means that is another actually solution, okay? Possible solution. Generally, a solution of a differential equation fulfills the following conditions. Number one, having the number of arbitrary constants equal to the order of the differential equation. Okay, guys? What about the second one? Consistent with the differential equation. So meaning when you substitute, it will make the differential equation a true statement. Okay? And then the last one, that solution of a differential equation must be free from derivatives or differentials. Okay, guys? So these are the three, generally, the conditions for a solution of a differential equation. Okay? So let us have some examples. Let's say I have this differential equation and then corresponding solution. For instance, if I have this differential equation x y cubed dx plus e to the x squared dy is equal to 0, if you're going to solve this differential equation, the solution that you will able to obtain, e to the negative x squared plus y to the negative 2 is equal to c. Okay? Where c here is an arbitrary constant. Later, I will explain to you what we mean by arbitrary constant here. Now, for the meantime, just believe that when I solve this, this is the solution. So when we go to solving differential equations, you will learn how to get this, okay? This equation. So this is in relation form. We assume that there is a function here that we can solve such that will satisfy this differential equation. Because as what we defined in the solution of a differential equation, we mean it a function. Although there are many cases that when you solve a differential equation, it is hard to express the solution in the form of a function, meaning y in terms of f of x, for instance. Most of the time, in the form of relation. We just assume that there is a function defined by this, okay? On an interval, for instance, a to b, okay? Open interval. Now, let's say the given equation is 1 plus tangent, the given differential equation, 1 plus tangent x multiplied by y double prime plus negative 2y prime plus 1 minus tangent x multiplied by y is equal to 0. Okay? So let's say that is the differential equation. if you're going to solve this differential equation, so again, if you're going to solve this differential equation, this is what you will get. Y is equal to A e to the x plus B cosine Y. Sorry, plus B cosine X. Okay, guys? So, where A and B here are arbitrary constants. Again, just believe that this is a solution to this DE for the meantime. Now, if we have a differential equation y triple prime, the expected solution for this y triple prime equal to 0 is given by this function y is equal to ax squared plus bx plus c, okay? Where a, b, and c, again, are arbitrary constants. Okay, guys?
Yes, po.
So, let's have the last one. Another example of a differential equation, y triple prime multiplied by 1 plus y prime quantity squared, and this is equal to 3 y prime times y double prime quantity squared. Okay? Now, again, if you're going to solve this is what you will get. X minus h quantity squared plus y minus k quantity squared is equal to r squared. So this is an equation of what? Of a circle. But of course, the one that will satisfy here is just part of this, no? Because what we want is a function, either upper part on the interval, for instance, open interval negative r to r, where r is positive. Possible also that a solution to this is a lower circle, a lower part of this on negative, on the open interval negative 2 to 2 also. Okay? So this is the solution of this last differential equation. Okay? Notice that all solutions can be expressed in the form y equals f of x. Although, as I said, because of algebraic manipulation problem, so it's hard to do that, no? But a solution to a differential equation must be what? Must be expressed in the form y equals f of x as much as possible, no? Solutions of a differential equation can be distinguished as explicit or implicit solutions. Okay, guys? So again, solutions of differential equations can be explicitly defined, can be implicitly defined. Like for instance, so the function here is implicitly defined because it is not expressed in terms of its independent variable. So no problem for this second and third. They are already in y equals f of x form, meaning it is now explicitly defined, this second and third. Okay? So they are called actually what? Nature or forms of solutions of a differential equation. Number one, we have explicit form. Or explicit solution. A function of the form y is equal to f of x. Okay? So again, nature or form of solutions of differential equations. Number one, explicit solution. That is a solution of a differential equation of the form y equals f of x. Okay, guys? While the second one, implicit form or implicit solution, okay? So when you say implicit solution, it is a solution of a differential equation written in the form g of xy equal to 0, or g sub 1 of xy is equal to g sub 2 of xy. So again, a solution of a differential equation written in the form g of xy equal to 0. So in other words, y is not clearly defined in terms of what? In terms of x. Okay? Y is not solved in terms of the independent variable. Or possible, the right side and the left side are both in terms of x and y generally. Okay, guys?
Yes po.
And we assume that it defines a function of the form y is equal to what? F of x. Okay? So that's what we mean by explicit and implicit solutions. So explicit solution is a solution of a differential equation written in the form y equals f of x. Implicit, it is written in the form g of xy equal to 0, or g sub 1 of xy equals g sub 2 of xy, with the assumption that it defines a function of the form y equals f of x. Although in most cases, we're not going to solve anymore because it's not that easy. Is that clear, guys? Okay. So let us have particular examples. So we have explicit solution, explicit solutions. Here, implicit solutions. Under this column, implicit solutions. So what are those some examples of explicit solutions of differential equations? So possible, we have this form. After solving a DE, you will get a form y equals ax cubed plus bx squared plus cx plus d. Okay? Where here there are how many arbitrary constants? 1, 2, 3, 4, A, B, C, and D. Okay? Another one, we have y is equal to c sub 1 e to the 2x plus c sub 2 e to the negative 2x. This is also written in explicit form. Y is equal to cosine of x plus b, then plus c. Okay? Where b and c here are arbitrary constants. R is equal to e to the theta multiplied by cosine for theta. Okay? This last one does not contain arbitrary constant. Later, I will be talking about those solutions that do not contain arbitrary constants anymore and those that still have arbitrary constants. And also notice here in this last example that the dependent variable is R and the independent is theta. Not all the time y and x are the dependent and independent. Possible to be other variables also. Okay? So again, these are explicit solutions of differential equations. What about for implicit solutions? So we have the following: x squared plus y squared. If you have a solution written in this form, this is in implicit form. So with the assumption that there is a y equals f of x that we can solve out of this. No? So, and then we have y squared plus by plus c times t is equal to 0. So here, b and c are arbitrary constants, and independent is t, dependent is y. So this is not written y as a function of x, therefore implicit. Okay? If you have dependent in terms of independent, that is explicit. Y to the 8 multiplied by 1 plus 4e to the negative 2x is equal to c squared. So another solution of a differential equation written in implicit form. Then the last one, we have ln of u squared plus v squared is equal to 4, then u plus v. Okay? So let's say it is said that u is the dependent, then v is the independent. And this is written in implicit form because u is not expressed in terms of what? In terms of v. Is it also possible that v is the dependent and independent is u? Okay, and if that is the case, there must be at least a function of the form v equals f of u. Okay, so that we can get out of this. So these are examples of solutions in implicit form. So there is a special solution identical to 0. If a function is equal to 0, then it is called a trivial solution, a special name for such solution. Trivial solution. So trivial solution is a solution of a differential equation of any differential equation that is identically equal to 0. That is identical to 0. Okay? So that is y equals 0 or f of x is equal to 0. Okay? For all x in a given interval. Okay? So that's what we mean by that. Obviously, that's the example. Y equals 0, f of x equals 0. If w is your dependent variable, w equal to 0, depending, for instance, to t. So that is a trivial solution. We mentioned of arbitrary constants. Okay? So when we say arbitrary constants, we mean those that are essential. Okay? So again, by arbitrary constants, we mean those that are essential. Okay, guys? So what do we mean by essential constants? Guys, anyone? Does any one of you know what an essential constant is? Children? Guys? Still alive?
Yes, sir.
So when you say essential constants, these are constants that cannot be reduced to a smaller number of arbitrary constants. So let's say we have 4. You can no longer reduce those 4 arbitrary constants into 3 arbitrary constants. Meaning, there are no 2 arbitrary constants, for instance, that you can still combine to reduce the number of arbitrary. So these are constants that cannot be reduced anymore to a smaller number of arbitrary constants. Okay, guys? So let us have specific examples. So let's say I have this equation. Y equals x ln A plus x ln B. A and B here are arbitrary constants, right, guys?
Yes, sir.
So how many arbitrary do we have? The way it is written, there are 2. But how many are essentials here? Are they both essentials? So let's see. I can rewrite this equation in the form of x, y equals ln of y equals x times what? Ln of A plus ln of B. Am I correct, children? But
Yes,
ln A and ln B, the sum of them is just a constant. But this is just a constant. Because A and B is constant, therefore their sum is also constant. We can reduce this, or you can name it into what? Into another arbitrary constant. Let's say equal to what? Equal to C. Okay? So hence we have y is equal to Cx. Where C is what? Where C is equal to ln A plus ln B. Since I was able to write ln A plus ln B, which originally containing two arbitrary constants into a single or simple constant, then arbitrary constant, we say that A and B are not essential. Only one arbitrary constant here is essential. Okay? And let's say it is C representing ln A plus ln B. So again, A and B are not what? Are not essentials or are not essential constant. Okay? So that is, there is one arbitrary constant is needed. Okay? Is essential here. Yeah. Is needed or is essential. Is that clear, children?
Yes, sir.
Guys? Okay, let's put S here. And let's just have another one. So let's say my equation is given by, or my solution is given by y equals a e to the b minus x, sorry, b minus x plus c e to the d plus x. So what about this one? How many arbitrary constants are you seeing, guys? A, B, C, and D, no? But are they all essential? Because when I mean arbitrary in the future, in the next that we're going to have, we mean essential. I will not give you a solution that is not, containing not essential arbitrary constants. Okay? So here, guys, what do you think? I can write this as what? A e to the b times what? E to the negative x. Am I right, guys? C e to the d times what, guys? Guys.
E raised to x po.
So we have e raised to x, okay? From laws of exponent. Am I right, guys?
Opo, sir.
Okay, so we now have y is equal to, or what can we say now, to e to the b? I mean a e to the b. Can we simplify this to a simple arbitrary? Yes, no? Let's say c sub 1. Then we now have e to the negative x, because this coefficient of e to the negative x, the whole coefficient can be considered constant, because e together with a and b are what? Are constants. A and b are arbitrary, while e is really a constant, approximately 2.71828, right? Guys? Okay? No. So what about the second term? So c e to the d, I can express that as what? Simply c sub 2, then multiplied by e to the x. So how many arbitrary constants do we have now, guys? Just 2. So meaning a, b, c, and d are not essentials. Okay? So therefore we say that a, b, c, and d are what? Are not essentials, no? Okay, guys? Got this, children? So, only two arbitrary constants are what? Are essentials here. Okay, only two arbitrary constants are essential. Okay? Which are C sub 1 and C sub 2. How will you know that an equation defining a function with that assumption is a solution to a differential equation, guys? So, that is about verification of solutions, okay? How to verify if an equation defining a function is a solution. Okay? So let us have the following examples. So show that x squared equals cy cubed is a solution of a differential equation. Derivative of y with respect to x equals 2y over 3x. So does this satisfy this DE on a certain interval? Let's say on an interval 5 to 8, on an interval open interval 0 to 10, whatever it is, okay? So how to verify this? How to show that this is really a solution? So let's have the proof. Okay? So we have x squared is equal to cy cubed. So this is the given equation, which we assume that it is a solution of what? Of this, no? So let's see if this will really be, which we are trying to show that it is a solution to this given D, no? So this is given. So again, this is the equation defining a function. We are trying to determine if it is a solution to this. So first step is you differentiate, no? How many times are we going to differentiate? One time only, because the given DE is just order 1. So we're going to differentiate this once only. Actually, because there is what? One arbitrary constant. Okay, guys? So differentiating the left, we get what? 2x. What about the right side? Guys?
3cy squared po.
3cy squared, no? 3cy squared. Multiplied by what? We still have to multiply this. Multiplied by derivative of y with respect to x. Remember, we differentiate this implicitly. So we have to multiply by the derivative of the dependent. Okay, guys? So from here, we're going to solve for C. Solving for C, we get what, guys? We have 2x. So what is C, guys? Solving for C. Guys. So let's solve for C from equation what? Equation 1. So from the given, let's call this equation 1. And this is equation 2. Okay? So from equation 1, what is the value of C, guys? C is equal to what?
Over y cube po.
Okay, so we have x squared over y cubed. Okay? Very good. Next, we're going to substitute this to what? To number 2. So substitution to number 2, we get from number 2, we have x times 2 is equal to what? 3c y squared derivative of y with respect to what? With respect to x. So 2x is equal to, what is our C, guys?
X squared over y cube po.
So x squared over y cubed times y squared derivative of y with respect to x. Or if you want, you can write this as y prime, no? Simplifying, we get what?
3 times x squared over po, plus
3x squared over y times derivative of y with respect to x, okay? So what about this? 2x, no, on the left side. Okay? Solving for derivative of y with respect to x, that is equal to, what's the derivative? We get what? Guys, we get 2xy over 3x squared. Am I correct? Simplifying this further, we have what? Equals 2x over 3x. Am I right, guys? Guys? So what do you notice?
Di ba 2y?
Sorry, 2y over 3x. So this is 2y over 3x. What do you notice, guys? This is the given DE. Since we were able to derive the given DE, so it means this is a solution to this DE. Okay? Or if you want, you can substitute this to the given DE. So that you will able to what? To get, for instance, an inequality. Okay? So, therefore, we say that x squared equals what? Cy cubed is a solution of a differential equation. Of the differential equation derivative of y with respect to x is equal to 2y over 3x. So again, if you will able to derive the given DE from the expected solution, then we say that such equation is a solution to that DE. Or if you want, you can substitute this to what? To this DE, and if you will come up with a true statement, then it is what? A solution to that DE. Okay? So let us have another one. Number 2. So we have and show that y equals hyperbolic cosine x. Are you familiar with hyperbolic cosine, guys? It's not a solution of the differential equation y double prime plus y prime equals 0. Okay, guys? So let's see. From the given function, y equals hyperbolic cosine x, we are going to differentiate this how many times? 2 times, because that's what we need in the DE. Okay? Or get the first derivative, hyperbolic sine x. Am I correct, guys? Still remember the derivative of hyperbolic cosine? What about derivative of hyperbolic sine? Hyperbolic cosine. Take note, positive ha? Unlike the derivative of trigonometric sine. Trigonometric cosine. The derivative of cosine is what? Negative. For hyperbolic, positive. Okay? Now, let's substitute this to the given DE. So, from the given DE, y double prime plus y prime equal to 0, we have okay? So what is y double prime, guys? Hyperbolic cosine. Last, what is y prime? Hyperbolic sine. Okay? It is equal to 0. Is hyperbolic cosine x plus hyperbolic sine x equal to 0 generally, guys? Is it equal to 0? False, no? Yan. So this is false. Therefore, it means this function does not satisfy the given equation. It does not make the equation a true statement. So hence, we say that what? Y equals hyperbolic cosine x is not a solution of y double prime plus y prime equal to 0. Okay? What if you're asked, what about y equals hyperbolic cosine of x is it a solution of y double prime minus y equal to 0? So let's check, okay? So given y equals hyperbolic cosine x, actually we obtained already the derivatives, no? What is y prime? Hyperbolic sine. What about y double prime? hyperbolic cosine. Sorry, guys. Okay? So, from this equation, y prime minus y equal to 0, this is the DE, no? Let's substitute. What is y double prime, guys? Y double prime minus y equal to 0. What is y double prime? Hyperbolic cosine, right? Hyperbolic cosine x. What is y? Hyperbolic cosine x also. Is it equal to 0, guys, the left side? Yes, no? Check. Therefore, we say that y equals hyperbolic cosine x is a solution. Solution of what, guys? Solution of y double prime minus y is equal to 0. Okay, guys? So, do you know now how to verify whether a solution, an equation defining a function with that assumption, defining a function, is a solution or not, guys? Guys?
Yes, po, sir.
Guys? Let's have the last one. We have number 3. Verify whether the given function is a solution or not. Okay? So my given function is y equals ln of x minus a plus b is a solution of y double prime plus y prime quantity squared equal to 0. So it's like in your algebra, no? Given, for instance, x equals 2. Is it a solution of x minus 2 equals 0? So when you substitute 2 to x, you get 2 minus 2 equal to 0. That's true. Therefore, x equals 2 is a solution of that equation. What about in this DE, no? Is this a solution to this DE, this function? Let's see, okay? So given this function, y equals ln of x minus a plus b. So we are going to differentiate this how many times? 2 times, because the given DE, maximum order 2, no? Or highest order. So we have to get up to the second derivative. Okay? We're going to differentiate twice, no? What about the derivative of ln of x minus a, guys? Derivative of x, 1. Derivative of a, 0, because a is constant. So 1 over x minus a, okay? What about the derivative of b? 0, because that is considered constant. What about the second derivative? That is quotient, no? Constant over function. Negative 1 times derivative of the denominator is 1 all over the square of the denominator. Okay? Is that clear, guys? So let's now substitute. So Given DE, we have what? Y double prime plus Y prime quantity squared plus 1. By the way, there is plus 1 here. Plus 1 in this given DE. Let's now continue. What is Y double prime? Negative 1 over X minus A quantity squared. Okay? Plus, what about Y prime quantity squared, guys?
Quantity 1 over x minus a quantity squared po.
Plus 1 is equal to 0. Is it equal to 0, the left side? It is false, right, guys? So what conclusion can we make out of this? Children, y equals ln of x minus a is not what? A solution, no? Of y double prime plus y prime squared plus 1 equals 0. Okay? That's it. That's how to verify. Is that clear, guys? Okay? We have this time elimination of arbitrary constants. Elimination of arbitrary constant. Arbitrary constants. What do we mean by elimination of arbitrary constants? By the way, this is to remind you that when I say arbitrary constants, I mean those that are essential. We can no longer simplify into less number of arbitrary constants. If there are two, they are two, okay? Not anymore less than two, the number of arbitrary. So what do you mean by elimination of arbitrary constants, guys?
I-reduce po yung lahat ng constant hanggang maging 0 po ba?
So when you say elimination of arbitrary constant, not that exactly. So we have to what? To get rid of the arbitrary constant, but of course we have to apply legitimate operations. So applying legitimate operations on the given, let's say, function. So we are trying to, that contains what, function that contains arbitrary constants. We are trying to find an equation free from arbitrary constants. And you can only do that if you're going to differentiate. So meaning we are determining a differential equation whose solution is the given function. Okay, guys? So again, by elimination of arbitrary constants, we mean the determination of what? Of a differential equation. Again, we mean the determination we mean the determination of a differential equation from the given general solution. From the given general solution. Okay, guys? From the given general solution, okay? So that's what we mean by elimination of arbitrary constants. So again, this is to remind you that the arbitrary constants here are essential. Okay? Contained in the general solution are essentials. Okay, guys? Yan. Now, what do we mean by general solution? So I mentioned here general solution, no? Solutions of a differential equation can be classified further into what? Into what we call general solution or complete solution and particular solution. So let us discuss that, okay? Before moving to or continuing elimination of arbitrary constants. We call these types of what? Solutions of differential equations, okay? And when I say differential equations, we mean ordinary differential equations. Our differential equations concern just an ordinary differential equation. We will not be dealing with partial differential equations. Solving them, we will not be having such, okay? So we have types of what? Types of solutions. So of an ordinary differential equation, of an ordinary differential equation, okay? Or simply differential equation, because we agreed that we will be dealing only with ordinary. Number one, we have what we call general solution. Okay, guys? What is a general solution? Anyone? Children?
Yun po ba yung given na solution sa question?
Not all the time that the given is in the form of general solution. So when you say general solution, it is a solution of a differential equation that contains a number that contains a number of arbitrary constants equal to the order of the differential equation. Okay? So again, when you say general solution, it is a solution of a differential equation containing a number of arbitrary constants equal to the order of the DE. Let's say my DE is second order. What do you expect for the number of arbitrary constants present in its general solution? 2. If we have 3 third order, so we have what? We have 3 arbitrary constants in the general solution. So that's what we mean by a general solution, okay? It is also called a complete solution, guys. So this one is also called complete solution. There are authors who use this term, but most of the books use general as a word for this general solution. Okay? For instance, if I have number 1, if I have a solution of this form, x squared plus y is equal to c. Oh, what about this, guys? What can you say about this? This is a general solution because it contains arbitrary constant, okay? 1 in this case. And it is expected to be a solution of what, guys? Since there is only 1 arbitrary constant. It is a solution of a first order DE. Okay? Yeah. So, and what DE is that, guys? This is a solution, is a general solution of what differential equation do you think, guys? 2x plus y prime equals 0. So this DE, what? Has a solution, x squared plus y equals c generally, no? Its general form. The solution of its general form. I mean, it's the form of its general solution, x squared plus c x squared plus y equals c. Okay, guys? The second one. What about the second one? I can have another example, by the way. So let's say I have y equals ln of sine of x minus c sub 1 plus c sub 2. So this is what? This is a general solution of y double prime plus y prime squared is equal, plus 1 is equal to 0. Okay? Now, so this is actually general solution of this DE. Notice that it is second order DE because how many arbitrary constants? We have 2. So as long as a solution of a DE has arbitrary constants, so it means it is still in general solution form. Okay, guys? But if you assign a particular value to the arbitrary constants or to an arbitrary constant, then all those arbitrary, you have assigned values. So that solution will become what we call particular solution. Is that clear, children? Guys?
Yes, po, sir.
By the way, take note that geometrically, a general solution means what? Geometrically, a general solution represents what? Children. Represents what does it represent, guys? Guys, represents what? a family or a collection of curves, no? Represents a family of solutions or curves. Okay? So that's what how we interpret general solution geometrically. What about the second type? We have particular solution. Particular solution is a solution of a differential equation free from arbitrary constant. No arbitrary constants anymore. Okay? But satisfying the differential equation satisfied by the general solution. So, and it is obtainable where you can obtain it from the general solution. Okay? So again, it is a solution of a differential equation obtainable from the general solution. After assigning specific values to the arbitrary constants. Okay?
Okay po.
So like for instance, by the way, it represents a particular curve, specific curve. Diba? It's a collection. They add the general solution. If you assign a value to arbitrary, let's say here C, you assign C equals 1. So you will have x squared plus y equals 1. That is a particular curve. It represents a particular curve, no? Or a specific curve. A particular curve. Okay? Is this clear now, guys? Examples. We'll stop right here after the examples, and then we'll continue, no? Because so that you have still much time to go to your next class. Okay? Examples of this, we have letter A, x squared plus y equals 1. If you assign c equals 1 in the general solution in number 1, we get what we call a particular solution. Is a particular solution of what? Of 2x plus y prime equal to 0. This DE is satisfied actually by this, no? And since this does not contain arbitrary constants, even a single one, so as long as there is no arbitrary constant satisfying a given DE, that solution is called a particular solution. Clear, guys? Guys? Guys?
Yes, sir.
Oh. What about letter B? So I have this general solution. Can you give me one particular solution? You have to assign values to C sub 1 and C sub 2. Okay? So let's say we have y equals what? ln of sine of x minus C sub 1. Let C sub 1 to be equal to 2. And C sub 2, positive 5. So this is a particular solution because no more arbitrary constant of what, guys? Y prime equals, plus y double prime plus y prime squared plus 1. Yan. Again, when you solve this DE, yan, it satisfies what this, no? So if I assign particular values to C sub 1 and C sub 2, that general solution now becomes what? Becomes, guys, a particular solution. Another particular solution, other particular. Can you give me one, guys? Guys, we have y equals ln of sine of x plus 1 minus 5. Y equals ln of sine x, meaning your C sub 1 is 0. Sine x. And then minus 3. Okay, guys? Any question with this before I leave? Guys?